Hi dear friends, good morning one and all. Myself Bhavsep Sonone, Assistant Professor, Department of Chemistry, Gokhale Education Societies, Arts, Commerce and Science College, Java, District Palghar. Dear friends, in the previous part of the video, we have discussed about outlines of syllabus of SYBSc Chemistry of Chemistry Paper 2 as per the syllabus designed by University of Mumbai. Dear friends, in that lecture, we have also discussed a detailed syllabus of chemistry paper 2, and then we came to know that there are total 3 units in the chemistry paper 2 for the semester 3. Unit number 1 based upon the physical chemistry, particularly this is chemical kinetics 2. Again, unit number 2 is based upon the inorganic chemistry, while unit number 3 is based upon the organic chemistry. Dear friends, today in this lecture we are going to discuss about the unit number 1, which is based upon the physical chemistry, entitled as chemical kinetics second. This is chemical kinetics second. Why this is so? Because if you remember about the first year of your graduation of the BSc, then this topic was also included in the first semester of the first year of graduation. That's why the extended part of this chemical kinetics that we are going to discuss here of the chemical kinetics, and that's why it is entitled as chemical kinetics second. Dear friends, in short, I would like to revise a recapitulation part of chemical kinetics of first year of the graduation, and in that topic we have discussed about, or you have already studied about the various terminology of chemical kinetics. But before this, what is chemical kinetics? Chemical kinetics is the branch of physical chemistry which deals with the study of rate of reactions and various factors affecting rate of reaction. So in the chemical kinetics particularly, we deals with the rate of reaction. Also we deals with the various factors which are responsible to decide the rate of reaction, and that branch is called as the chemical kinetics. Definitely in that topic it is also included that what is molecular rate of reaction, order of reaction, and different types of order of reaction. But one important statement that is deciding the rate of reaction is the concentration of reactor molecule. How many number of reactor molecules are responsible for the rate of reaction, that much number of reactor molecule is the order of reaction. But in order to derive the equation for the order of reaction, we are using the law called as the rate law. According to the statement of rate law, the rate of reaction at any instant is directly proportional to the concentration of reactant at that instance. And in that lecture, or in that topic, it was a very important factor which was responsible to decide the rate of reaction, and that factor is a concentration of reactant. Definitely in addition to the concentration of reactant, another factors are also responsible for the rate of reaction that we will not talk here, but it was one of the factors which was deciding the rate of reaction. Dear friends, in this topic today, in this lecture, we are also going to talk about the rate of reaction. But here, before discussing the rate of reaction, definitely we are going to talk about the particular theories here which are responsible to explain the rate of reaction. But here, before discussing the rate of reaction with the help of various types of the theories, we will talk about the type of reaction that we are going to discuss, that we are going to study in the chemical kinetics second in this part of the video. Friends, in this part of the video we are going to talk about the different type of the reaction called as the complex reaction and not the simple reaction, because in the first year of the graduation we totally discussed about the simple reaction, and definitely here we peoples are restricted for the study of rate of reaction of complex reaction and not the simple reaction. So before discussing the rate of complex reaction, we should know what is complex reaction. Complex word itself indicates that definitely these are the reaction in which more than two or more than three reactant molecules are responsible to decide the rate of reaction. It means that these type of the reactions are having order greater than 3. This is very simple, and that's why here we are able to explain this. We are able to explain this complex reaction. So these are the reaction in which reactant molecule pass through various or different transition states. So these reactions are involving the various transition state or number of transition state due to their bond breaking and energy distribution factor. So definitely number of transition state will be different in this type of the reaction. Again, this type of the reactions consist of more than two or more than three steps. So definitely the number of steps are more in this type of the reaction, as it is involving a more number of reactant, and that reactants also responsible to decide the rate of reaction. Or another definition or another way by which we will be able to explain, we will be able to define the complex reaction. The reaction whose order is greater than 3, that reaction is also called as the complex reaction, because already we know what is zero order reaction, first order reaction, and second or the third order reaction. And whenever the order of reaction becomes greater, it becomes complex reaction. It is not simple reaction, and in case of a complex reaction, it is very difficult to define the mechanism of reaction as well as the rate of reaction. And one of the example of the complex reaction is the decomposition of nitrogen pentoxide. So this is one of the example for the complex reaction. So complex reactions, in short, we can say that these are the reactions having order greater than 3, and it consists of more than 2 or more than 3 steps, and it is involving various transition state due to their bond breaking and energy distribution factor. So this will be sufficient for you to remember about, to know about the complex reaction. So what are the different types of complex reaction? Actually there are 3 types of the complex reaction. The first complex reaction is called as the opposing reaction. This opposing complex reaction are also called as the reversible reaction. I hope opposing you know very well. So whenever this words indicates that opposing. So whenever there is a forward reaction, and if it is opposed by means a backward reaction, definitely this type of the reactions are. So here both the conversion will be there, forward and backward convergence will be there. So these opposing reactions are also called as reversible reaction. Definitely we are going to discuss about these reaction one by one in detail in the next slide. But before this, we should know what are the different types. So first type is called as opposing or the reversible reaction. Second type is called as the consecutive or the sequential reaction, and the third one is called as the parallel or the side reaction. So these are the various names and the another names of these types. So we are discussing these 3 types of the complex reaction, and we are also interested to define their rate also. So the first one is opposing, or it is also called as the reversible reaction. So I hope you will be able to know about this opposing reaction. Okay, this opposing reaction or the reversible reaction, what does it mean actually? Okay, let me update this, as you should be able to see this. Okay, thank you. So opposing reaction or the reversible reaction, these are the reaction in which reactant molecules are able to form the product, but these reactant molecules forms the unstable product. These reactant molecules forms the unstable product. So whenever you will compare the stability of reactant and the stability of product, the stability of product will be smaller definitely, and the product will not be stable. So once the product is formed, as it is unstable, that's why it will again decompose back into reactant. So this is the characteristic of this opposing reaction and the reversible reaction. So here in this type of the reaction, reactant molecule forms the product, but this product unstable, and that's why it will not remain in the same state, it will not remain in the same form, and it will try to undergo decomposition, and it will decompose back into reactor. That's why initially reactant get converted into unstable product, but initially the rate of forward reaction will be more, because though the product is unstable, but then and then product formation will take place, and after the formation of product it will again reconverted or decompose into the reactant. But initially whenever we will start the reaction, the rate of forward reaction is more, and this rate of forward reaction will decreases with the time, and rate of backward reaction increases. So this is very simple. Initially rate of forward reaction is more and rate of backward reaction is smaller. Why this is so? Because initially the concentration of reactant is greater while that of product is smaller, and that's why the rate of forward reaction will be more and the rate of backward reaction will be smaller. But as the time proceeds, the concentration of reactant decreases while the concentration of product increases. Hence, the rate of backward reaction increases with the product or with the concentration of the product. And there will be one stage, that condition is called as the equilibrium condition. So here you can just consider, here the rate of, suppose this is the rate of forward reaction goes on decreasing and the rate of backward reaction goes on increasing, and there will be the one condition at which the concentration of reactant, means the rate of forward reaction, becomes equal to the rate of backward reaction, and that condition is called as the equilibrium condition. And at the equilibrium condition, always remember that the concentration of reactant and the concentration of product becomes equal. So this is the case here. I will try to show you this rate of forward reaction and the rate of backward reaction becomes equal at the equilibrium state. How it is possible, that I will show here. Suppose this is the one reaction that is called as the opposing reaction or reversible reaction, general reaction. A get converted into product. So this is the conversion of reactant into product with the rate constant K1. But this product is unstable. That's why it will again decompose into the reactant, and the formation or the decomposition of B, product B, into again reactant, its the rate constant is K2, while the formation of B from K1 is, means rate constant of forward reaction is K1 and rate constant of backward reaction is K2. So initial concentration of reactant will be small a, that of the product will be 0 as no reaction started. After some time, suppose X is the amount of product formed, then the concentration of reactant left on reactor, it will be A minus X. Already we have studied in the first year of the graduation how this can be considered here. So rate of reaction is what? Change in concentration of reactant or product to the change in time. So delta X, this is the change in concentration of product, delta T, it is the change in time. So this ratio is called as the rate of reaction, which will be equal to K1, rate constant of forward reaction, into concentration of reactant. What is concentration of reactant after time T? A minus X, minus rate constant of backward reaction, K2, into the concentration of this. Now it will, for the decomposition, it will act as a reactant, into the concentration of B as a reactant, and that is X at a time T or after some time T. So rate of K1 is the rate constant for the forward reaction and K2 is the rate constant of backward reaction. So difference of these two will give you the rate of reaction. And at equilibrium, you know very well, the concentration of reactant and product remains same, or it becomes equal, means there is no change in the concentration of both the species. It means that change in concentration becomes 0. So definitely this term will become 0. So rate of reaction delta X by delta T becomes 0, and that's why after the simplification of this term, so this whole term becomes equal to 0. So if I will transfer it K2 into X on this side, it will become positive. So X upon A minus X is equal to K1 upon K2. but this X is the concentration of what? This X is the concentration of product, and A minus X is the concentration of what? It is the concentration of reactant. Means the concentration of product to the concentration of reactant is equal to their, or is equal to the rate constant of forward reaction divided by rate constant of backward reaction. Both are the rate constant. So instead of these two constant, we have taken another constant, that is called as K, and this is called as the equilibrium constant. And this equilibrium constant, this equilibrium constant is the ratio of what? It is the ratio of concentration of product to that of reactant. So this equation can be used to find out the equilibrium constant for the opposing reaction or the reversible reaction, that I will be able to show here with the help of this graph. Here this plot indicates how there is change in concentration of reactant A, and the change in concentration of, how there is a change in concentration of reactant A and product B. So as the time proceeds, the concentration of reactant decreases while the concentration of product increases. So this is the general thing, and that we can discuss, that already we have discussed about. As the time proceeds in the chemical reaction, the concentration of reactant decreases while the concentration of product increases. But after some time, or at the equilibrium condition, the concentration of reactant and product becomes equal, and that condition is called as equilibrium condition. I hope you will be able to understand about the one of the type of the complex reaction called as opposing or the reversible reaction. And the example is the dissociation of hydrogen iodide into the formation of PH2 and I2, because the whatever products, hydrogen and iodine, these are formed here, these are again unstable, so these again reconverted into hydrogen iodide. So whenever the hydrogen iodide gives the formation of hydrogen and iodine, these are again reconverted into the hydrogen iodide. So that's why this is the reversible reaction. So this is one of the type of the complex reaction that we discussed here, called as opposing or the reversible reaction. Second type of the complex reaction that we can discuss here is called as a conjugative reaction, or which is also called as a sequential reaction. Conjugative words itself indicates sequence, so one after the another. So this type of the reaction, this type of the complex reaction consists of number of steps or the number of sequence, and that's why in this type of the reaction the final product is formed. By one or more than one steps. So it consists of more than one step, and that's why these reactions are also called as a sequential reaction. So it means that initially a reactant get converted into intermediate, and later on this intermediate will give you the formation of product. So here we can say this A is the reactant here, B is the intermediate, and C is the final product. So for the conversion of reactant into product, we are having some intermediate, and this total conversion involving more than one step. So first step is the conversion of reactant A into intermediate B, and the second step will be conversion of intermediate B into C. So rate constant of conversion of A into intermediate B is K1, and rate constant of conversion of intermediate into C is K2. So these are definitely the initial concentration of A will be A0, that of the B and C at the start of reaction at the initial time will be 0, and after some time, suppose the concentration of remain unreacted is A, that of B is B, and that of C is nothing but the C. So therefore total concentration of reactant, at any time will be the concentration of A plus concentration of B concentration of C. It means that suppose it is initially 100%, and suppose after some time it becomes that is nothing but the 60. It means that out of 100, 60 remains unreacted, means another 40% get converted to B and C. It may be possible that it is supposed 10, and now it becomes that is nothing but a 30, or it may be that is nothing but 20, or it may be that is the here it will be 30 and it 10, but the sum of these two will be 40. So here definitely as the time proceeds, the concentration of A decreases continuously, while concentration of C increases continuously, because this is the final product. Initially A will get converted into B, and this B get converted to final product. So as the time proceeds, as the reaction proceeds, the concentration of A decreases continuously, and the concentration of C increases continuously, while the concentration of intermediate initially increases and then it will decreases. So this is nothing but the actually graph that you will come to, that concentration of A continuous decreases, concentration of product continuous increases, concentration of intermediate increases and then decreases. So this is the I hope you will be able to, because this is the just intermediate, it will not remain in the reaction. This is the reactant, definitely it is going to be decreases with the time, and it is the product, so definitely the concentration is going to increase with the time. So I can show you, this is the graph which indicates the concentration of reactant A decreases, concentration of reactant A decreases continuously. Here you can see decreases continuously, while the concentration of final product increases continuously. Let me clear once again. The concentration of reactant A decreases continuously, while the concentration of final product C increases continuously, and the concentration of intermediate B initially it decreases and then it will decreases. Initially it will increases and then it decreases. I hope we will be able to make clear that concentration of reactant decreases continuously, concentration of final product increases continuously, while the concentration of intermediate initially increases and then it will decreases with the time. And one of the example for the this consecutive or the sequential reaction is the first order consecutive reaction, in which dimethyl ether get converted into methane and formaldehyde with the rate constant K1. But this is the intermediate, these are the intermediate. What happens actually, this formaldehyde is again converted into another product with the rate constant H2 and the carbon monoxide. So definitely this is the gas, all are the gases, but this formaldehyde is again converted into another, which are the final product of this dimethyl ether, and this is the hydrogen and carbon monoxide. And this concentration of intermediate is also important, and the maximum concentration means at this point can be calculated with the help of rate equation. Change in concentration of intermediate B to the change in time, means the rate of this reaction, is equal to rate constant of conversion of A into B minus rate constant of conversion of B into C. So K1 into concentration of reactant A minus K2 into concentration of intermediate B. So this is the one of the important type of the complex reaction that we discuss. Next is the parallel reaction. Parallel means simultaneously. These are also called as side reaction. So in this case, what happens actually? Reactant molecules follows more than two paths or more than one path to form the different product or to form the more than one product. As it follows more than one product, definitely it will form the more than one. As it follows more than one path, it means that it will also form more than one product. Suppose here I will say show you here only one reactant A is there. In the by means of an first path, it gives the first product B, and by means of a second path, it gives the another product C. So rate constant for the conversion of A into B is K1, while the rate constant for the conversion of A into C is K2. So K1 and K2, these are the two rate constants. But here the out of two product, one product is called as the major product, another one is called as the minor product, and that major and minor proportion is depends upon their stability. So this major product is more stable and minor product is less stable. So that's why rate constant for the major product is greater than the rate constant of minor product. So minor product is the unstable product. So their stability definitely depends upon their energy that we will discuss in the graph. But the overall rate constant for this side reaction or the parallel reaction is the sum of rate constant of major product plus rate constant of formation of minor product. So whenever you will take the sum of these two rate constant, you will get a overall rate constant for this parallel or side reaction. So already I told you K1 is the rate constant of conversion of A into B, and K2 is the rate constant of conversion of A into C. So this is very simple. So this is nothing but the graph that indicates the formation of major and the minor product. So initially A is the reactor, so this A get converted into B, A get converted into B with the rate constant K1. So this is the rate constant, and this A get converted to another product by means of different path, and this A get converted into another product C with the different path having rate constant K2. But here if we consider the energy of product C and the energy of product B, definitely the energy of product B is smaller than the energy of product C. It means that energetically C is having more energy than the B, and you know very well, whenever the energy and the stability these are compared, then because of the higher energy of C, it is less stable, and because of the smaller energy or the less energy of B, it is more stable. So definitely both the products are having different energy, different stability, and these are formed by means of a different pathway or the different mechanism, and definitely C is a less stable, that's why it's a minor product, and B is more stable, that's why it is major product. Here one of the example by which we can show you this ethyl bromide reacts with the KOH. Definitely it gives the formation of two products. One product is ethene, another one is the ethanol product, and both are nothing but definitely this is the two product. Out of these two, definitely one will be major product, another one will be minor product. Definitely sorry. So here this ethyl bromide reacts with the KOH, and it gives the formation of two products, particularly one is the ethene, another one is the ethanol. Definitely the nature of this KOH is responsible to decide the stability of these two products. But definitely if it is alcoholic KOH, then definitely you are getting the different product, and if it is alcoholic KOH, then definitely you are getting a different product. But whenever you are getting the formation of this product, definitely there is a mixture of both the product, either in the alcoholic KOH or the KOH, aqueous KOH. Then it gives the mixture of these two products. One will be stable, another one will be unstable. Means one will be major product, another one will be minor product. So dear friends, in this part of the video we have discussed about the complex reaction, and we have also discussed about the various types of the complex reaction. Particularly we have also discussed about their rate equation, and we have studied the change in concentration of reactant, intermediate and the product with the help of system of the graphs. I hope you got the idea about complex reaction and various types of the complex reaction. Particularly these are opposing reactions, conjugative reactions and the parallel reactions. So in the next part of the video we will discuss about the next part of complex reaction. So thank you once again. So we'll resume again in the next part of the video. Thank you.